Okay, hello, good morning, everyone. Welcome to Curiosity Students Question the World and Connecting Taiwan. And our topic for today is Roving and Flying, Searching for Life on Mars. I'm your host, Iris, from National Jiao University, and it's our honor to have Mr. Hogg with us today. And I hope you enjoy the exciting journey as we explore the wonder of Mars together. Before we started, and I would like to provide some brief overview of our program. Curiosity students want question the world and introduce our team. In the following section, to benefit our audience, I will switch to Mandarin to explain the process of the Q&A section. 欢迎各位教授、同学、观众来参与由好奇学生大哉问、大同大学、辅英科技大学、铭传大学、东吴大学、静宜大学、辅仁大学、台北科技大学、慈济大学、嘉义大学、东海大学、台北市立大学、中原大学联合主办的好奇学生大哉问连结台湾系列专题讲座。感谢现在线上参与的各所国内外学校学生，也感谢一级人士各位伙伴的热烈响应。大家知道好奇学生大哉问的主旨是什么吗？好奇学生大哉问的主旨是建立一个活动平台，邀请海内外专业人士透过每月一次的专题讲座，将他们的知识经验与大家分享，让同学们能聆听前辈们的演讲，激发同学们的好奇心，自主学习并提出问题。线上的同学知道好奇学生大哉问的主旨是什么吗？大胆提问才能成就非凡未来，所以我们愿意提供丰富的提问奖金，也希望大家可以踊跃参与。我们的活动会安排在每月第3周的星期五早上10点10分到11点45分，以线上视讯的方式呈现。学生参与方式只要透过在演讲前的大胆提问，追踪我们的官方社群，社群连结都可以在聊天室中查看。在 KKTix 报名活动中提出问题，演讲者会参考提问问题规划本次的演讲。在演讲中呢，填写问题表单，让演讲者在 Q&A 环节回应问题。欢迎以及感谢的时候，大家可以按荧幕右下角的回应来鼓掌与致谢。演讲结束后，欢迎参与好奇学生大哉问工作团队，学习团队合作能力。好的，那接下来让我们先请我们的节目主办人刘登凯博士为我们说明提问奖金的部分。我们有请刘博士。
好，谢谢主持人。在我讲之前，介绍我们的这个颁奖的东西信息以外，我先用英文说一下啊。Hey Robert, we're so grateful to have you join us here and as our special invited speaker. Robert and I have been working together since 1996. That's a long time ago. He's very well known in our community, and so I'm so grateful to have him. And I also want to thank you, President Huang, 澎湖大学校长黄友平校长来介绍我们的嘉宾的。那黄校长是有名的学者，是 IEEE 的 Fellow， 而且得到许多不同的奖项。谢谢校长。Hey Robert, I'm going to switch to Mandarin and discuss the award. Usually we encourage the student to ask questions and to motivate them of their participation. And we offer the cash awards so that they have no excuse not to ask questions, especially with you as such an excellent speaker. So 各位同学，我们现在跟大家介绍我们的有关的这个提问题的奖金。我们有2个部分，一个是在你们在报名的时候你们问的问题，那我们同样选出来3名，第1名给1000，第2名给500，第3名给300。那另外一个部分就是说是在我们的演讲者嘉宾这个Robert 他演讲后以后呢，那我们会希望同学呢踊跃提问题，因为这个机会非常难得。那他是一个非常非常资深，而且很有在这个火星方面呢来讲的话，是一个非常有经验而且有知识的一个演讲者呀。我希望同学抓这个机会多问你们的问题好，那我就同样的也是一样，我们有这个1000块钱第一名，500块钱第二名，300块钱第三名。那我这个把我们的现场交给我们的主持人，谢谢主持人。
好，谢谢刘博士的说明。接着在这边跟同学讲解一下节目流程。我们在11:05会结束演讲，接着会开始我们47分钟的 Q&A 活动环节。如果听了讲者精彩演讲后有任何疑问，都欢迎同学透过聊天室中的提问连结传送你的问题。我们将现场选出3个好问题给予提问奖金，也会选出演讲前报名表单中的3个问题，共6个得奖名额。那问题可以包含针对演讲者 Mr. Robert Hogg 的专业领域以及他的心路历程方面来提问。那请得奖同学活动结束后留下来加入得奖赖群，确认进入赖群后再离开。于是或是没有上线听演讲的得奖同学，奖项就会被取消。那麻烦各位同学配合以利我们后续的奖金颁发作业。提问的部分还是可以透过中文提问，但提醒各位，本次的演讲将会透过英文的形式呈现，大家可以点选荧幕最右边有3个点，开启字幕哦。本次的演讲主题由 Mr. Robert Hogg 主讲的火星表面巡查与飞行，寻找火星上的生命 Roving and Flying, Searching for Life on Mars。那让我们邀请澎湖科技大学黄友平校长为我们介绍我们今天的演讲嘉宾 Mr. Robert Hogg。那我们有请黄校长。
Okay, good morning, ladies and gentlemen. My name is Youping Huang, President of National University of Science and Technology. I'm so honored to introduce today's distinguished speaker, JPL Mars Mission Project Managers Robert Hogg, to deliver a very excellent, we can expect to a very excellent speech. 各位女士、各位先生，大家早安我是国立澎湖科技大学校长黄友平。那因为探测火星是不是有水源，一直是各国科学家他们努力的一个重点。包括我们在2004年跟我们主持人刘登凯刘博士一起合作实况转播2艘 MER Mars Exploration Rovers Opportunity and Spirit的这个精彩的登陆实况，那时候在台湾引起很大的轰动，包括就是 TVBS 有实况的转播。那我们今天非常荣幸能够邀请到Robert Hogg 来为我们做这个专题的演讲。因为呢Robert Hogg 他不只是在这个 JPL 担任高级工程师，另外呢最主要就是我们以前在学习的过程当中都认为火星就是一颗红色的星球。那为什么火星是红色的星球？因为我们远远看它真的是火红的一颗星球。那么呢探测这个火星的任务大家都一直在积极的进行。所以呢Robert 从1997年就开始加入 NASA， 然后呢他具有开创性的这个研发的成果，特别是在这个深空一号 Deep Space One， 他在这个任务当中呢担任这个 software engineer。那在这个期间呢，他取得这个整个太空探险上面非常重要的一个成就，就是拍摄了历史上最接近彗星的这样的一个影像。各位知道我们平常拍照都已经不容易，你要在太空能够拍到清楚的彗星影像这更是难上加难。所以呢Robert 他参与了 NASA JPL 这很多特别的这些任务他的专长特别是在机器人还有这个行星的探险上面。所以呢他开发了 JPL 上面 这个所谓的城市的机器人系统，以及呢最有名的就是一个类似像我们 Spider 蜘蛛人这样的一个机器人，那个叫做 Spider OK， 那所以呢从2020年开始，那他担任这个Project Manager， 特别是在探测火星上面。那他针对了我们大家熟悉的毅力号，还有呢这个探测车跟机智号直升机。那大家都没有去过火星，所以当然没有办法实际上看到的。可是从很多的这个演练当中、模拟当中，我们让人类的这个梦想能够一步一步的去达成。所以呢，借由这些 MER， 我们就可以去找到火星上面这些古代的生命的迹象，特别是如果能够找到水源，那这个对人类的这个科技的进展呢，更是往前迈进了一大步。所以呢，我们今天特别高兴有这样的一个机会能够邀请 Robert 来做演讲。So now, ladies and gentlemen, let's give Robert a big applause to deliver his speech on roving and flying, searching for life on Mars. Thank you.
Let's welcome Mr. Robert Hogg to start his speech.
Thank you very much, Professor Wang, Dr. Liu, and Iris, and the CSQW team. I really appreciate your welcoming me here, and it is my honor. So thank you very much. I'm going to talk about something that I'm very familiar with and proud of. I've been working on the Mars 2020 project for now over 10 years. And we created the rover called Perseverance and the helicopter called Ingenuity. And so I will give you some idea of what it was like, particularly operating these two robot explorers on the next planet over. So I'll start with one of my favorite quotes from Arthur C. Clarke. He wrote some science fiction books, and sometimes science fiction gets turned into reality. And he said, any sufficiently advanced technology is indistinguishable from magic. And I think you'll see by the time I'm done that in a very short amount of time, some magic was created on Mars and continues to be created across this world. The projects that the Jet Propulsion Lab and NASA have sent to Mars are on the screen here. And we've actually been putting landers on the surface of Mars since the mid-1970s. There were two Viking landers that landed in one spot, and they had a robotic arm. And then many years later, in 1996, we landed the first rover. It's very small, the size of like a microwave. And actually, that was the first week that I started working at NASA at the Jet Propulsion Lab, the week that the Sojourner rover landed. And then in 2003, we launched two more rovers that were larger and were designed to last 3 months. They were supposed to run for 3 months on Mars, and they're the size of a table. And they exceeded our wildest imagination, and they lasted 9 years and 15 years, which was really amazing to us. We didn't think they were going to last that long. Then we landed a lander in 2007, Phoenix, and the next rover that I worked on is Curiosity, and Curiosity is the size of a small car. And that is similar for Perseverance, the mission that I am running now. Perseverance used a lot of the same designs as Curiosity, and similarly, it uses 6-wheel drive, and a lot of things are different, but we were able to use the same designs. So lots of missions on the surface, and we've had many missions in orbit around Mars, and so we're using 4 different orbiters or more to communicate to our rover as they orbit the planet. Here is just a little bit more of these 4 rovers. There's the small one in the upper left, and then Spirit and Opportunity are in the upper right, and then Curiosity, bottom left, and then Perseverance, the one that I will be talking about today. So we have sent 5 rovers to Mars and some number of landers and, of course, several orbiter missions. And all these were done at the Jet Propulsion Lab in the Los Angeles area. The Perseverance rover mission objectives are really 4. And I'll focus on the middle one, but they are geology of Mars, astrobiology, biology, and for the first time, trying to get samples in tubes to be brought back to Earth so that we can use all the instruments in all the universities of Earth to see what we can find. And then we also ran an experiment to generate oxygen from the air on Mars, from the Martian atmosphere, to prepare for humans on Mars later. And that was a very successful experiment. Our rover weighs 1 ton, 2,000 pounds, about 900 kilograms. And it has a rocker bogie suspension system so that when each wheel goes over a rock, the whole rover stays very level. It doesn't get too tilted. We have 7 different instruments. On the remote sensing mast is a very capable stereo pair of cameras with different color filters and a laser spectrometer. A laser can zap a rock and look at the vapor, the particles coming off of the rock with a spectrometer by bouncing light off the smoke and then seeing what the rock is made of. And so then we can see what rocks in the area around the rover are composed of without having to use the arm or anything else. We have a 7-foot, 2-meter robotic arm with 2 spectrometers at the end of the arm that are the most capable instruments that have been sent to Mars. We have a weather station, and MOXIE is the oxygen generation experiment. And then lastly, we have a radar, just like on a submarine, and it's pointed down. And we send fire off the radar every 10 centimeters as the rover is driving to see what the solid surfaces are underneath the rover. So here's a few more pictures of the different instruments. This gold box is the oxygen generation experiment, and these are what the instruments look like when they're done and ready to be put into the rover. These are some wind sensors that are on the weather station, and we have a whole drilling mechanism at the end of the robotic arm to be able to get the samples, which I will tell you all about. So Curiosity, the previous rover, had great instruments, and its main purpose was to find soil or parts of Mars that could support life, like grow a potato plant or something like that. And that was successful. With Perseverance, the goal of the mission is to find signs of past microbial life, microbes, so small organisms like bacteria or viruses or like lichen that grows on a rock, and then to get samples of possible signs of life. We don't have the instruments to know for sure, and bring the samples back. And that's why we have to bring them back, so that we are sure about what we find. So we designed an entire new robotic system to take samples from the drill bit and store them in titanium tubes. And we get about 5 to 7 centimeters of rock core. And we have 43 tubes on the rover. And this whole mechanism is in the rover's belly underneath. And there's another robotic arm that manages the tubes. And this is what it looks like when we're getting a sample and then processing the sample. At the end of the robotic arm, once the scientists find an area of Mars that they find very interesting, we've taken lots of pictures and spectrometers, information. We unstow the robotic arm and then use a hollow drill bit to get the rock core, and the tube is inside the bit. And then we take the tube and put it into a processing station that rotates the tube inside the rover. And then the tube is, the core sample is measured and imaged, several different pictures, and then it's sealed so that it definitely can't open until it's all the way back to Earth. And then it's stored in its container. And right now we have about 20, let's see, we've taken about 27 samples, and there's about 15 on the rover, which I will explain later. And so this is the tube being stored. So this is an animation, but we built this whole system, and we sent it to Mars in 2020, which was an interesting year to finish a robot and send it, and it was very successful. So after a team of several hundred people worked very hard for many years to put this whole thing together, this is what it looks like on your screen here. It's in our clean room, and all the instruments are inside, and everything is ready, everything is working. We've tested everything. We made sure the whole thing works together, and we have a hope of success once it arrives on Mars. And right here is a little additional traveler on our mission. That is the helicopter, which I will show you later. Here, these are the blades of the helicopter. They're about 1.2 meters wide. So then we take the rover and the helicopter and we attach it to our landing engine. There's 8 Mars landing engines, and that's what's used for the final part of the landing, which I will show you. So this is where our landing site was picked. There's a large crater on Mars called Jezero Crater. A very large impact happened millions of years ago. And on the upper left part of the crater, right here, you can see a river flowing into the crater. And that river collected material from 50 kilometers and flowed that material into Jezero Crater, and that's this, we call that the delta front. So scientists from all over the world picked this landing spot among hundreds of landing spots, and they talked about it for several years and narrowed it down to 8, and then 3, and then this landing spot. And so we wanted to land the rover safely near this flow and then drive over and start taking samples, because we know water flowed through there millions of years ago with all this material. And so this is an animation of how you land a 900 kilogram rover on Mars. So you start with a heat shield, slow down from 10,000 miles per hour, and then deploy a very large parachute and slow down to hundreds of miles per hour, and then release the heat shield, and then the rover drops from the parachute and the back shell, and the 8 landing engines fire and slow down. And we've used a visual radar and guidance for it to autonomously land itself. And the reason it has to do all of that by itself is because Mars is very far away. It's between 30 and 250 million miles. And the way we communicate to our rovers is over radio, which travels at the speed of light. And so the round trip, if we were telling it what to do while it was landing, would take somewhere between 3.5 minutes to 22 minutes. And the whole landing takes 7 minutes. So humans cannot be in the loop when we're landing. The flight system and the rover have to do everything by themselves, all those different steps by themselves. And then we cross our fingers and watch the signal coming back to see if it worked. On this particular mission, we upgraded our system for landing and used terrain relative navigation, where we have images stored in the rover, and as it's coming down with the rockets and with the parachute, it's taking pictures and comparing the pictures to the images that it has on board with a field programmable gate array, FPGA. So very fast processing, hardware processing. And in the image on board, it knows where all the obstacles and the hazards are. And so it can compare and then divert as it's landing to get away from the obstacles. All right, so that was the animation of what was supposed to happen. And this is
we are starting the straighten
what
up and
actually
fly
happened.
right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Applicate indicate chute deploy.
The navigation has
That's the
confirmed
parachute
that
coming
the
out.
parachute has deployed, and we are seeing significant
And
detail.
the parachute has a very strange pattern. And to make a very long story short, we needed a pattern that you could that's different to your eyes to see how the parachute is doing while we're landing. And so the team that made the parachute made this pattern, but they put a fun, we call it a cookie, a secret message in the parachute, and they didn't tell anybody about it. And I will tell you what the message is at the end of the presentation. So if anybody has any guesses about this message, you can put your guess in the chat.
In the velocity, our current velocity
Okay,
is
so we released the
400
parachute,
meters per
and this is the heat shield dropping
Heat
away.
shield set.
This mission
slowed
is the
to
first time
subsonic
we've had
speeds, and the heat shield has been
a
separated.
camera
This allows
capturing
both
everything
the radar
about the
and the cameras
landing.
to get their first look
We
at
used
the surface. Current velocity is
commercially
145
available
meters per
cameras
second
looking
and an
down
altitude of
and
about
looking up.
9
And then
9.5
we
kilometers above
downloaded the
surface.
images over many months through the orbiters and got all the images back and made this landing sequence. This is real imagery of exactly what it would look like if you were landing on Mars in real time. That
Net
is
filter converged.
surface of
Velocity
Mars.
solution 3.3 meters per second.
And the team
Altitude.
does not know if we're going to be successful or not. So we're on the parachute, and then we release the back shell and the parachute right here.
Of timing of the
And
landing
then
engine.
we intentionally do a diversion, a move to the right to get away from the back shell and the
Back
parachute
shell
right
Current
there
velocity is
to make
83
sure
meters
that
per
we
second
don't
at
have
about
a collision.
2.6 kilometers from the surface of Mars.
And then we continue down on the landing rocket. And as you get closer to the ground, you'll see the dirt kicking up
We have started our constant velocity
and the
accordion,
dust
which means we are
on
conducting
another
the sky
planet.
crane.
On the upper left is a camera looking up at the landing engines, and a camera on the landing engines looking down at the rover. And then when we sever the connection to the rover, one of the camera images cuts out, and we tell the landing rockets to fly away and crash as far as possible from the rover.
About to conduct the sky crane maneuver.
And this
Sky
is
crane maneuver has started.
exactly how it happened.
About 20 meters off the surface.
On February 18th, 2021 at 12:55 p.m.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready
And we
to
were
begin
very,
seeking the
very
sands
happy.
of past life.
That the 7 minutes worked. So you can imagine spending 10 years of your life, or 7 years of your life, or 5 years, and you're going to find out if you have a job the next day and you'll get to explore another planet, or you've just made another crater on Mars, and that's all. So this is we had one of the orbiters divert from its orbit, and it took a picture while we were landing. And here is the parachute and the spacecraft while in the middle of the landing. And this is the hypersonic parachute opening at 30% speed. Okay, so because I'd worked so much on this rover and had different areas of responsibility, I got to be the mission manager for the surface. So I got to take over the mission 20 minutes after we landed. And so this is a picture of my desk, and this is the first picture that we got down of our new home. And this is a picture of our rover safe and sound on the surface. And then we took some pictures with our exceptional cameras on the mast, and it was really amazing because all the scientists on the team, I'm not a scientist, I'm an engineer, but we were all very excited to see this area that we get to explore. Really amazing stuff. So the first thing we needed to do was make sure, after all that the rover was still working, that the wheels were working, the arm was working. If the wheels aren't working, we're just stuck in one place, then it's not really much of a mission. So this is the very first drive. This is the drive that we commanded the rover to do. So we told it to drive forward and then drive to the right and then turn 180 degrees and then take a picture of the ground that it drove over. So that's the very first drive we did. And here is the picture at the end of the drive. And if you look very closely, you can see it looks like a rover fell out of the sky and landed right there on that spot. And that's exactly what happened. We landed an alien on Mars. We needed to test out the sample and caching system in the arm. And this is an example of taking the camera at the end of our arm and going closer and closer and closer to the ground and taking pictures. And this is amazing to me because just to give you an idea of how far away Mars is, with my wife, I go on trips driving, around our area in the country. And so we like to go up north 300 miles, and it takes us 6 hours to go 300 miles. So if you got in a car and started driving towards Mars at 100 kilometers per hour, depending on where Earth and Mars are in their orbits, it would take 200 to 500 years to drive to Mars one way. So Mars is very far away. And here we get to see images that are taken of this interesting rock, and the images are taken from millimeters above the ground. And so this is an example of technology magic where we can see this on another planet that close and see, look for interesting things there. Okay, so this is what happened with the helicopter. The helicopter is stowed on the bottom of the rover. And the first thing to do is just to get it safely off the rover, which was much harder than we thought, because if we didn't get the rover away from the helicopter within 40 hours, then there wouldn't be enough power on the solar cells, and the helicopter would die. We successfully got the helicopter down off the belly and moved the rover, and then we took a selfie picture with it's like a family picture of our robots, both successfully on the surface. And this is how we take a picture of the robot with its own arm. The arm is taking a bunch of different pictures with the camera at the end of the arm, and then we stitch all the pictures together into one image. So here's our celebration selfie. So then it came time to try to fly this helicopter. And humans have never flown anything, powered flight, on another planet before we tried it with this helicopter. So the whole purpose of this was a technology demonstration. And if we got one successful flight where it took off and it landed, then we get to declare success and say the Ingenuity, the Mars helicopter, was completely successful. So we drove the rover 50 meters away and then did a test spin of the helicopter blades, and everything looked like it was working. And then we filmed the helicopter from the rover from 50 meters away. And this is the very first flight attempt on another planet ever. So she flew up into the air 3 meters, and then we had her rotate 90 degrees and then hover for a little while. And I was there in the control room thinking, okay, now please land. We have successfully in the air. Now please land, please land. And she came down and successfully landed. And so now we can say that humans have flown on another planet. And there are many more helicopter ideas now that are in the works as a result of this work. Here's what the team looked like when we first took flight.
Earlier today, Ingenuity should have autonomously performed its first flight attempt on Mars. Now the team is ready to receive the data that will tell them whether we've made history.
This is downlink. We are beginning to see data products.
Rotor motors appear healthy. All actuators appear healthy.
Ingenuity is reporting having performed spin-up, takeoff, climb, hover, descent, landing, touchdown, and spin down. Altimeter data confirms that Ingenuity has performed its first flight of a powered aircraft to another planet.
We can now say that human beings have flown a rotorcraft on another planet. Let's get back to work and more flights. Congratulations.
So we were all very happy. I worked with all those people for many years leading up to that. It was quite a moment. So this is a picture from the helicopter. This is the first picture that we got to see from the air on Mars. And you can see the rover tracks as the rover came over to drop off the helicopter and then drive away to a safe distance. And you can see the helicopter's legs here in the picture, and there's the shadow. Here's another picture of Mars from the air. So we got to see Mars from a whole new view using Ingenuity, the helicopter. Here's my favorite video of the helicopter. So pretend that you are one of the first people to stand on Mars. And you sent your helicopter out to go explore. And you're standing there looking over this hills and waiting for your helicopter to come back. And I'm going to speed this up back and forth. You can see a dust devil. See the little dust tornado on the right side. Mars has some weather, so there's a little tornado going by. And then after a little while, your little aerial scout comes back from its mission and flies back to home base. And then in this flight, we told her to fly up to reach a new altitude record. And so you can see it fly up over the mountain and then fly back down and land. So after that first flight, we flew the helicopter further and further and faster and higher, and it kept working and kept working. And I led a team to figure out how to use the helicopter and the rover together, which took a lot of work because we didn't intend to keep the helicopter going. And we ended up flying the helicopter for 72 flights. 72 flights, not just one, over 3 years. This is what it looks like from the helicopter's navigation camera as it flies over the surface. So this is from about 10 meters high, 12 meters off the ground. And so it would fly for about 2 minutes, and the longest flight that we did was about 700 meters in 2 minutes. It takes the rover 3 days or 4 days to drive 700 meters, but the helicopter was able to do it in 2 minutes. And here's just another couple shots of the helicopter in action. And then we'll move on to the rest of the story here. That's tracking the ground to see how it's flying in the air. And this is showing dust coming up as it's flying. Okay, so I told you about the oxygen generation experiment, and it was very successful. It's embedded in the side of the rover, and it takes carbon dioxide, CO2, right out of the air. Mars, I think, has about 70% carbon dioxide, and then it uses some electricity and a stack of metals to convert the carbon dioxide into oxygen, O2. And so over about 10 or 15 experiments and runs, we were able to generate about 20 minutes of oxygen that a person could breathe. So a very successful experiment. So we can make a bigger version of this for people to use on Mars, and we can generate oxygen right out of the air for people to be able to breathe. So back to the main purpose of the mission, we're looking for ancient microbial life. We already know that there's no cows on Mars, no trees, no buildings. We have pictures of all of Mars in very high resolution. We know there's nothing running around on Mars or growing there, but we're wondering if we can find signs of life from when water was flowing on Mars in the past. I am not a scientist, so these are just my own ideas about the science aspect. I do not represent NASA in this. These are all just my ideas. But this is one of the first attempts for us to find life on another planet. We're looking for life that happened a long time ago, but it's still life. And we might be able to find any hint, any clue of life on another planet, not just Earth. And so we think there might be, and we don't know, we haven't found it yet, very small single-celled organisms or bacteria or something. So the science team found this first interesting spot, and we decided to abrade it and clear the surface of the top surface of the rock, and then take a picture very close to it and analyze the spectra. And this is what it looks like when we grind the top surface of the rock off and then blow it away. We get to see these amazing, amazing pieces of material that have all kinds of things in there that we can analyze with the spectrometers. So that was our very first drill attempt, and then we got a sample in one of the tubes, and this is what the hole looks like after we get the sample. And here's the rock with the hole in it. And this is our drilling bit, and there's the sample inside the bit. And here's the sample imaged inside the rover. So this is the very first piece of Mars that we find very interesting that will be brought back at some point in the future. So we decided to celebrate by taking another selfie. So here's our rock with 2 samples taken, and a job well done by the rover. So we landed here, and this is again where that flow coming over the crater wall is. So we wanted to come all the way over here. So we did a lot of driving over 3 weeks, and we made a very fast driving system. This rover can drive 5 or 10 times faster than Curiosity. And this is what it looks like when it's driving itself across Mars with no humans helping it. We told it, go 200 meters in this direction and then go 200 meters further north. And so it's avoiding rocks and looking for cliffs and making sure the wheels don't get stuck. And if there's any problems, then it just stops and it phones home for help. So we drove all the way over to the Delta, and we started sampling these flows, and we got a bunch of different samples. And this is just some of the samples we got. And you can see all these different really interesting pieces of material that we have collected in these tubes. And so one of the things we wanted to do is make sure that there's a way to pick up some of the tubes and bring them back if the rover has a problem. So we decided, and so the reason we took 2 samples of each rock there's 2 samples out of this rock, so we can drop one sample on the ground and then keep the other one in the rover. So if the rover ever has a problem, we can send a mission to go get the sample tubes off the ground. So we spent a bunch of time dropping 10 of our sample tubes in one area of Mars so that they could be picked up later. So here's one, and then there's another one, and there's all 10 sample tubes are along these rover tracks sitting on the ground. And they will just stay there for years and years until we come and pick them up with another rover, if needed. That is the backup plan. But the main plan is to keep all the samples in our rover and meet up with another mission several years from now and hand the samples to them. And I'll show you that in a little bit. So here's the rover doing a selfie with our first sample on the ground, ready to be picked up, the sample tube. So this is one of the possible ways that we're thinking about bringing samples back. It's not very simple. You need to send a spacecraft with a lander or with a robot to go pick up the tubes, and then our robot docks with that spacecraft, and then it has a rocket in it, and that's the first rocket that would ever launch from another planet. And you launch those samples in the nose cone of the rocket into orbit around Mars, and then you send another spacecraft to pick up the samples out of orbit and bring them back to Earth. And if that's what we ended up doing, this is what it would look like. All the samples are in the nose of the rocket, and this would be the first rocket ever to launch on another planet. And then we release a little package of samples, and this little package is floating in orbit by itself around Mars, 200 million miles away, and we need to know where it is and rendezvous with it with another orbiter, and this is what that might look like. So that spacecraft would then return that package to Earth and then release it with a small heat shield, and it would just fall into a specific location in the desert where we would land it. And then we go over and get the package out of the heat shield and take out the tubes. And then we've returned all these samples that we spent more than 3 years finding on Mars and packaging up and getting them ready to be brought back. And then those samples will be sent all around to different labs on the Earth and analyzed to see if we've done a good job of finding something interesting over there. So back to the message in the parachute, because the parachute team needed to make a visual image that had differences in it. They decided, you know what, let's hide a message in there with a code. And so with binary, it's it's binary code, ones and zeros. They spelled out the motto for JPL, D-A-R-E, dare, M-I-G-H-T-Y, dare mighty things, T-H-I-N-G, dare mighty things. And on the outside ring is GPS coordinates for the Jet Propulsion Lab. So everybody knows where to find us. It's the north GPS and the west GPS coordinates. And it didn't take very long for people out on the internet to figure out this message. So it took a huge team to pull this off, and we are still going strong. This is 1 year, one picture that we took of the Mars 2020 team, and I got to be in there and be part of it. And now today I get to be the mission manager in charge of running the mission every day, every week with the whole team and the science team looking for and finding these samples. So big thank you to the whole team. And now we will move on to questions, if that sounds good to you, Iris.
Yes, thank you. So thank you, Mr. Hogg, and for your wonderful speech. So let's move on to the Q&A section, which will last about 47 minutes. And before that, I would like to briefly explain the process in Mandarin. So 我们现在进入 Q&A 环节，到11点40分。如果现场有任何疑问，都欢迎使用工作人员背板上的 QR code 或是聊天室中的 Q&A 表单连接问问题。若您的问题被挑中，线上参与的观众可以开麦克风跟讲者互动，可以追问一题。那如果你没有问题的话，也请说 Thank you, Mr. Hogg。如果你是在现场实体现场提问的同学，当我喊你的名字的时候，请到台上拿麦克风，站在镜头前跟讲者互动。互动当下也可以追问一题，如果没有问题的话，也请说 Thank you, Mr. Hogg， 并回到座位。那接下来请播放第一个问题。第一个问题是来自建议大学西文系的张艺兴同学，他的问题是：机器有问题的时候是如何维修的 ？How do you repair it if there's any problem with the rover? So, yeah.
Very good question to start with. Well, when we have a problem with a computer here, you can just send the technician over and turn off the computer and turn it back on, and usually everything starts working again. But we have no technicians on Mars, so we have to make our rovers very carefully, and we have to make redundant systems. So we have not just one main computer, but two main computers, and 2 copies of the electronics board that's running the motors, and 2 copies of all the cameras that we're using. So if one of the computers has a problem with the software and it freezes or gets a blue screen of death, then the rover automatically switches to the other computer and boots from there. And then we work with it to try and figure out what the problem was. So we use redundant processors and systems, but also we have to make these so that they work every time and they're not going to have a problem. So we're very careful in our design and writing the software. And then we do a lot of testing. We test each part a lot and then put the parts together and then test those a lot and then put the whole rover together and then test that a lot, exactly how we're going to use it to make sure it's not going to have any problems. So we cannot repair it. We need to make it so that it can recover or not need any repairs for its whole lifetime.
OK， 那这位同学，请问有在线上吗？请开麦克风跟镜头。你好。
嗨。
你有要问任何问题吗？或是可以向讲者致谢？
我想要问他是怎么进去 NASA？
Okay, so she want to ask an additional question, a follow-up question, that is, how do you get into NASA to get this job? Yeah.
I'm glad you asked that question. You study a related area of technology, and the usual areas are mechanical engineering, computer science, electrical engineering, astrobiology. We have scientists on our team, or aeronautics engineering. And you work hard at those and do internships and work on projects that are similar to what we do. And then the way I did it, and one of the good ways to do it, is you do an internship at one of the NASA centers, and then work hard at that, and then work your way up from there.
Okay. Thank you, Robert.
My pleasure.
谢谢同学。那我们到第二个问题，谢谢同学的提问。那第二个问题是来自静宜大学资工一的苏玉婷同学。那他的提问是：请问这些机器的晶片是在 NASA 内部由设计单位制作，还是外包给其他公司的晶片外包给其他地方的晶片公司 ？So are the chips used in those machines designed and manufactured internally or by the NASA design units, or they're outsourced to other chips companies? That is his question.
The answer is both, depending on what we need. We have custom designed boards that run the motors, for example, and they're using different outsourced or subcontractors to make the chips. The main processor that was used is a radiation hardened processor, which NASA didn't make internally. We outsourced that to, I think it's Intel. I'll have to check on that. But so it's one of the big chip companies. So there's lots of companies and chip companies that if they make a product or a chip that meets our needs, that can withstand radiation and handle shock and vibration and is light and works well, then we use them. And then we make sure they test them very well, and we test them very well, and then they go on our missions.
Thank you. 这位同学有在线上吗？可以开麦跟开镜头与讲者互动。苏玉婷同学，请问同学有在线上或是在实体教室内吗？So So she comments in.
下一题的话，你先暂停编辑一下。
Okay, she cannot turn on her mic. Do you have any follow? 请问你有任何追加的问题吗？ Do you have any follow-up question, or you can just comment? 可以就是在聊天室中。OK. 他没有任何问题 ，so no question, no follow-up question, and thank you. So we're moving on to the next one. 那我们请看下一个问题，这是来自大同大学的林冠化，来自资工系。他的问题是，火星探测车使用的光谱分析与样本检测技术是如何克服低温与低压环境的挑战，并确保数据准确性。How do the spectral analysis and sample detection technology currently used by Mars exploration rover overcome the challenges of low temperature and low pressure environments to ensure the accuracy of the data? That is the question.
What a fantastic question. Absolutely correct. our rover experiences temperatures from about 0 Celsius to about minus 80 Celsius every day. At night, it's minus 80, and during the day, it's 0. And there are seasons, so it gets warmer and even colder. And so that's when.
So sorry, the mic is turning off.
Looks like I got muted somehow. All right, can you hear me, Iris?
Yes.
Okay, so that's why it's so hard for a computer to work on Mars, because of the big temperature swings. Also, there's lots of radiation. And as the question mentions, there's much lower pressure. The pressure is 1/100th of Earth pressure. So I'm not an expert in the manufacture of the instruments, but we use chips, and we build boards that specifically can handle the cycling of the temperature up and down every day for at least a year and a half. And so when the instruments are made, all the electronic boards, sometimes they have heaters to make sure they don't get too cold, but we put them in a thermal testing chamber and make the temperature go up and down, up and down, up and down, over and over, to make sure that nothing bad is going to happen with the instrument. And then the measurements still work pretty good over there, because there are different types of light, which still works well. There's a little bit of dust in the environment, but low pressure doesn't affect spectrometers very much. And then lastly, we have a big 10-meter diameter space simulator chamber where we can put the whole robot inside, pump out the air so that it's 1/100th of the pressure, make the temperature go down to minus 80 or minus 120, and then test the robot and test the instruments and drive the robot a little bit and test everything to make sure that it's going to work in Martian temperatures and Martian pressure.
OK， 这位同学，请问这位同学提问的同学现在在线上吗？可以开麦与讲者互动。
好吗
Hello.
Excuse me. Okay. Hi.
Hello.
Okay. I have another question, but I need the host to translate for me. Okay. 我还有一个问题，就是火星探测车它用的应该是，就是我查到资料应该是用 RTG， 就是一个放射性的一个核电池，然后作为它的动力来源。那我想问的是说，在它这样的环境下，它要怎么做它的温度管理跟能量的平衡？
Okay, so the question is, he has to do some research that the battery is used from the sources from RTG. I believe that is how it's called. And the question is how to manage the temperature and balanced under this kind of environment.
Okay, so if I understand the question correctly, so we have different heat sources. And when we have an electricity generation machine, so we have a nuclear engine that generates electricity constantly for years, and then we use that electricity to run heaters to keep electronics warm inside the rover so that they don't get too cold. And if the engine generates too much heat, we let some of the heat out into the atmosphere to make sure that the rover doesn't get too hot or different instruments get too hot. So we have thermal sensors at different parts of the rover that are monitoring the temperature. And then depending on whether they get too hot or too cold, we turn on the heater in that area, or we let out some heat if needed.
请问有回答到同学的问题吗？
有。Okay.
谢谢。
Thank you, Robert.
Thank you.
Professor.
Thank you for your question and the answer also. So the next question is, 来自静宜大学大众传播系的王福轩同学，他的问题是：火星上有哪些我们可以利用的矿物？What minerals are there on Mars that we can use? That is the question.
I am not a scientist, so I can only tell you what I've heard. But we've found lots of minerals on Mars or materials that exist on Earth too. We've found carbon and the results of volcanic activity and the results of dust settling over time. And we found oxygen trapped in water and in carbon dioxide. And we have found ice, large amounts of ice, which is really good news because we can melt it and turn it to water to drink it, and then use it to make oxygen and hydrogen, and we can breathe the hydrogen or breathe the oxygen and use the hydrogen for rocket fuel. When we were first exploring Mars with robots, we were wondering, and this was part of Curiosity's mission, if the dirt and the surface of Mars is too acidic or salty to be able to support life or grow things. And Curiosity found different areas of Mars that don't have too much acid, don't have too much salt, and you could just put a little glass dome on the ground, fill the little glass dome with oxygen, and plant a potato plant on that spot and give it a little bit of water, and it would grow out of that ground using the minerals in the ground. So a lot of the same material and minerals and water and things are there that are here on Earth that we could use for growing, for breathing, and for drinking.
Oh, that's an interesting fact. 这位同学有在线上吗？
这里有听到吗？
是，请提问。有任何追加问题吗？
No, thank you, Robert.
Thank you.
Thank you. And we have another question. 好，北科大车辆3的同学，他的问题是：火星车可以控制其垂直与滚动运动吗？如果不幸翻覆，是否有可能自我恢复 ？Is a rover able to control its heave and roll? And if it's unfortunately this flip over, is it possible to self-recover?
Yes and no. So, yeah, very good point. As we're driving over rocks and driving up hills and driving down things, the rover experiences tilt, and the wheels, the suspension system help. Like some of the wheels go over a rock, and then the next wheel goes over a rock, and the first wheel goes down, and then the last wheel goes over. And the rover has gyros and accelerometers, and so it can measure how much tilt it has all the time. And every day when we send commands to it, we send commands to the rover once per day and tell it to go up that hill and then get the arm ready the next day. And so when we tell it to go up the hill, we tell it if your tilt goes above 24 degrees, because we've been looking at that hill with the stereo data. If the tilt goes over 24 degrees, then just stop. Don't do anything and wait for instructions the next day. So the rover has automatic safety limits so that hopefully it will never flip over or cause a problem like that. And it will stop what it's doing and phone back to us for instructions long before it actually would flip over. And finally, if the rover ever flipped over on top and it was upside down, then the mission is over. It cannot put itself right side up, and it does not have the ability to flip itself back over.
Got it. 请问同学有在线上吗？
Hello, could you hear me?
Yes.
Okay, thank you for your answer. And here I have another question to ask about the design of the rover.
Ready.
Okay, so I'm a little bit curious about the center of gravity of this of the rover, because you have a long arm at the front, and I'm a little bit curious about if there is a counterweight designed at this rover to counterbalance if the arm is stretched out.
That is a very insightful question. The center of gravity was carefully considered because we don't want the center of gravity to be too high and make it too top heavy, but we also need lots of the center of mass to be high off the ground so that the wheels and the belly have lots of clearance as we're driving over rocks. So you're right, the center of gravity is off the ground and it could be lower, but then we wouldn't be able to navigate over rocks as well. The robotic arm is very heavy and it has a very heavy load at the end of it, but it's definitely not enough weight such that when the arm is extended, that the rover would tilt forward, tilt forward too much. However, we do have an issue, which the team was discussing last week, where when we're extending the arm, because the arm weighs so much, sometimes the rover can shift a little bit, and we get concerned if the robotic arm is very close to the ground, and then there's a sudden a little tilt forward that we could run the arm into the ground. And so we do need to be careful when we're doing arm operations to make sure that there isn't a little shift that that's accidental that could cause a problem. But in general, we can move the robotic arm around as much as we want, and it doesn't cause too much of a problem with the rover center of gravity or its tilt. So we don't need a counterbalance for the robotic arm.
Okay, thank you for your answering.
Thank you for your excellent questions.
谢谢这位同学。那我们看下一个问题，是来自大同大学的工业设计学系。他的问题是在设计开展的过程中，如何发现问题，验证产品的可行性、是非或是地形适应。那 So the question is, during the design process, how would you discover problems, verify the feasibility of the rover, such as taxi flight or terrain adaptation? That is the question.
This is a very key point, and this is how we make rovers and landers and spacecraft that actually work without having to have a technician to fix them. We have engineers who have some good experience, and they learn from the folks who were making the rovers in the 70s and the 90s. And we have lessons that we've learned when we're making these rovers. And so some of the lessons are that when you make one of these, you need to make a test program that simulates as much as possible what's going to happen when it's actually on Mars or on another planet. And so, like I was describing, when you make one of the instruments, they make the instrument and they make a prototype, and then they put it into a temperature chamber and a vibration chamber and make sure nothing breaks. And then we put that instrument at the end of the robotic arm, and the robotic arm has been tested in all the different ways that we're going to use it. And if there's a problem with a cable that's too short, then we find out, although the cable should be the right length. And if the motor control board did the wrong thing, then we have a chance to fix it and then make a new design and then test it again. So we have we build into our schedule some design iteration time to fix and then remake something and then test it again if we need to. Hopefully most of the designs that we use computer-aided tools to design are going to work well, and we're using electronic components that are tough. And then when we put it all together, we make sure it's going to work well by testing in the space simulator chamber that I described. And then also we have an outdoor yard at JPL that looks a little bit like Mars. It's got rocks and hills. And when we have the driving system working together, we go drive around and drive over rocks and make sure it can automatically avoid rocks. And then we take our driving system out to the desert an hour away and we drive it all over the desert. So we try and test each piece exactly how it's going to be experiencing the environment, and then we put the pieces together and then test all those exactly how they're going to work in the environment until we have a complete rover, and then we test that whole thing and make sure the driving is working and the arm is working and the instruments are working. So this is a very key part of our process is the testing and the cycle of being able to test over and over as we build the rover up.
Okay, so 刘应婷同学在线上吗？请问有任何追加问题吗？
Thank you, Robert. It sounds like you guys have very many extreme tests. Thank you for your sharing.
Thank you for the great question.
Okay, thank you. And the next question, 我们来看下一个问题。是来自淡江大学电机系资讯组的同学，他的问题是：人类未来有可能有一部分的人移民到火星上吗 ？Is it possible for that some people might immigrate to Mars in the future?
I think anything is possible. These are my opinions, but I will say I think the reason that we're so interested in Mars is because it's the closest thing like Earth that we've found. If you look at this picture behind me, you could be, in the desert somewhere with a little bit of dust in the air, and you can walk around there, and and also it's one of the closest planets to Earth, and so I think we're going to get there. It's been a very short amount of time since we got people on the moon, and we've been able to send these robotic spacecraft to Mars, and that's why we send robots, because it's a one-way trip. We don't have to bring them back, because it takes a lot more rocket fuel to bring them back and to send the water and the oxygen and exercise equipment for people. But I think it's important, even though I've been working on robots for years and working on these Mars robot explorers, I think it's important to get humans to Mars at some point. And there's a lot more interest in that now than there was 10 years ago or 20 years ago. And so I think interest will grow. The word immigrate is very interesting there. It's going to be a big challenge just to get 2 people on Mars for a few weeks and then get them back. So that's going to be the first big step. But in the far future, I could imagine we've got, like I mentioned, we've got ice there, which we can generate oxygen. We've got a lot of sand. You can make glass from sand. So I can imagine in my mind a big glass dome or habitats that have oxygen generated in them, and you can grow things. We know that now. So the soil and the dirt there can grow stuff. But it's going to take a lot of support for somebody to live there for a while, and a lot of work in building machines and construction and factories that can self-sustain there. And that takes a lot of work in getting all the equipment there. So in the far future, I can imagine it, but there's some major steps to be accomplished first.
Okay. 那张瑞祥同学在线上有任何追加问题吗？
在。没有。Thank you, Robert.
Thank you.
Thank you. 好，那我们再讲解一次我们的 追加我们的活动 Q&A 的说明。那鼓励各位同学，如果有任何提问的话，都可以透过聊天室的连接发送问题。我们现场会选出3个好问题给予奖金。提问奖金可以针对演讲者的专业领域或是他的心路历程方面来询问。那得奖之后呢，就可以加入得奖赖群，确认加入后就可以离开。那我们最后也会有演讲结束后的追加15分钟的提问时间。如果有任何疑问的同学，都可以留下来向讲者询问。那欢迎大家填写提问表单哦。那我们现在来看下一个问题。下一个问题是来自北科大车辆系的同学，如果人类要移民火星，要如何先改变火星的大气环境呢？ If humans were to immigrate to Mars, how would we first need to change Mars' atmospheric environment? That is the question.
This is a tough problem. From my understanding, my simple understanding, Mars did have an atmosphere millions of years ago, and then inside the planet, over time, the core shifted and changed and evolved maybe a little bit, and that made the magnetic field that Mars once had reduce. Earth has a fantastic magnetic field that keeps things trapped and provides some protection, and Mars does not have that. And once that shift happened, the atmosphere of Mars kept getting scraped away by the solar wind from the sun, and eventually reduced to this very, very light atmosphere that's there now that can't support humans. So the simple, easier solution is to make only indoor living possible, or suits for outdoor living. And that is very realistic. You can send buildings and make buildings and pump the buildings full of oxygen and make indoor growing chambers and stuff. I can imagine that we as a species could come up with some ideas to maybe terraform Mars's atmosphere on a very grand scale. There's been some very wild ideas about that, about, setting off explosions in the ice caps and trying to artificially create a lot of greenhouse gases to capture some of the atmosphere. But I have not heard anything that's realistic yet. And so maybe in the far future, we'll be able to figure out something like that. But in the nearer term, indoor living is possible first.
Okay. 刘翔宇同学在线上吗 ？Hello。
有在。
请问有任何追加问题吗？
喂，有听到我的声音吗？
有听到声音。
我想问一下，就是如果到时候要创这个地球时间应该不一样。
不好意思，可以重复一次问题吗？
就如果人类真的移民火星的话，那是不是要创造一个火星时间？因为火星跟地球的那个时间应该不一样。
Oh, so that's an interesting question. He has a follow-up question that is, should we change the time or to create a time just for Mars if we immigrate? So like Mars time, something like this. That is the question.
Wow, that's great. Yes, we should. And I will tell you why. Mars rotates 40 minutes different than Earth. So Earth and Mars are rotating at slightly different speeds. So sunset and sunrise on Mars is different by about 40 minutes every day. So when we first started this mission, we needed to sleep on Mars time to be very efficient so that the rover was doing as much as possible morning to night. So we on Earth had to get up at sunrise on Mars time and go to sleep at sunset. And that was different 40 minutes every day. So once a month, I and my team would be getting up at 8 a.m. and 8:40 a.m. and then 9:20 and then 10 a.m. and then 1 p.m. and then getting up at 9 p.m. and then getting up at 2 a.m. and then repeating that every month. So I agree with you. Whenever we have people on Mars and colonize Mars, Mars time, the time zone will mean a shift of 40 minutes every day, forever.
Thank you for your response.
Okay, thank you, Mr. Robert.
Thank you.
Okay, thank you. 那我们进到最后一个问题。This is our last question from 空军官校航空电子系。人类对于太空的探险是否已经到达极限，或是还有任何向外探索的可能 ？Has human exploration of space reached its limits, or is it still possible to explore further? That is the question.
I have some remarks in my my final remarks along this line. So it's a great question. Absolutely not. Have we reached a limit? It feels to me like we're at the very beginning, and things are going very slow, and they're going to speed up, and humans on this planet are going to spend more time and work on this more and more together, and it's going to get faster and better and farther, and we're going to keep finding interesting things out there in the solar system, and then be looking at the next star systems that are close by. So it is very possible, and we're nowhere near the limit.
那我们这位同学，请问有在线上吗？魏晨同学，来自空军官校航空电子系的同学。
有，我在线上。
是，请问有任何追加问题吗？
我可以直接用中文吗？
好，可以。
就是以现在的技术，还有没有其他可以再往外？就是因为目前我们知道的只有还没有到海王，就是甚至还没有到海王星，还有就是现在有没有什么技术是可以再更往外一点的可能这样？
So the question is there any current technology that can help us to explore further, like just based on the current situation?
Not realistically, but it's being worked on.
Oh, it's being worked on.
And we need help. The best idea that I have heard, and it's an idea that's maybe some initial work is being done on, is to make, because of all the progress that we have made with small electronic portable devices that have very, very fast computers and gyros and accelerometers and phones, sorry, not phones, cameras and video cameras and microphones, we could take a very small electronics package with all those sensors and figure out a way to get it going very fast, like a solar sail that uses the solar wind from the sun, or directed lasers to a sail, like a very large sail that can continually speed up the micro spacecraft. And the great thing about space is there's very few particles out there, so there's nothing to slow you down. So if you just start speeding up a spacecraft with just a little bit of push over many, many months or many, many years, it goes faster and faster and faster and keeps going faster. And maybe we can get a small spacecraft going at 1/10 the speed of light with a lot of work, a very small spacecraft with a lot of push. And then at 1/10 the speed of light, in 40 years, we could send that spacecraft by the next star that's closest to us and take pictures and send the pictures back at very low resolution and see what's over there.
OK， 那感谢这位同学的提问。请问可以请同学开麦克风？
Thank you.
Thank you.
Thank you. Thank you for the question and the answer. And that is our last question. 这是我们的最后一个问题，我们的时间 Q&A 环节已经结束了。So thank you, Mr. Hogg's wonderful talk about NASA and the Mars exploration. And just as Mr. Hogg mentioned at the beginning, like quoting from the authors, the clock, and the advanced technologies like the magic. So today's talk, just with all these amazing and precious images from Mars, just showed us how incredible it could be. And thank you again for Mr. Hogg's inspiring presentation, and it has filled us with excitement and hope for our future. So thank you again. And now we would like to invite Mr. Hogg to share his takeaway message and to present his closing remarks with our students. So yes, please, Mr. Hogg.
Thank you very much, Iris, and thank you, everybody. I really appreciate the welcome and the excellent questions and your attention and interest. The message that I will leave you with is the following. In my view, we have just begun to explore just our solar system. Humans have really only been going up off the surface of the Earth in the last 60 years. Think about when people first went to the moon, and when we first sent robots to the nearest planet was 60 years ago. That is less than one lifetime. Think about that for a second. In one lifetime or less is all of the exploration of the solar system that we have done so far. So we're just getting started, and we're going to find many more amazing discoveries out there. You've seen everything that has been happening with Mars. We're launching a spacecraft to Europa, which is the 4th largest moon that's around Jupiter. That should be launching later this year. And we have a whole moon campaign by sending people back to the moon and establishing a moon base there, which is good practice for Mars. And speaking of which, eventually humans will set foot on Mars and then continue to explore Mars. And if you have interest, your generation, the people who are your age, will be those first explorers on Mars. It's not going to be me and people my age. So if you have interest in this area, you're in exactly the right zone of age and interest, and when all the technology is coming together to be able to do the first Mars missions and then see what happens next. So we're living in the most exciting time in history, in my view. When I was just getting into stuff like this when I was a boy, there were only a few very expensive computers around that nobody had access to and cost too much money. There were no laptops, there were no smartphones, and there was no internet when I got started on this stuff. So look how far we've come in the last 20, 30 years. We have all that. We have a worldwide planetary communication system, and all the ideas and possibilities that can be learned are infinite using what we have now. Each of you have infinite capabilities and possibilities. Really, I'm being very honest. You have the possibility of an infinity of ideas that you can work on and things that you can create and projects that you can do. So I believe that we eventually need to become a multi-planetary species, not just be on one planet. And it might take a very long time, and it needs to happen at the correct speed of development. And, you know, we need to do a long-term campaign of work and progression and steps. But today we might have started that campaign already. This hopefully will be the very beginning, and you're living right in the middle of it. So thank you for your time and your interest, and I can't wait to see what you achieve over the next lifetime of time and technological advancement that you have at your fingertips. And I'm very excited about us all exploring the solar system some more, and then heading out and seeing what else is out there. So thank you very much.
Thank you so much, Mr. Hogg. Thank you for your exciting and encouraging message. So let's give Mr. Hogg our biggest round of applause to express our sincere appreciation for his insightful speech and invaluable contribution today. Okay, so let's move on to our last session. I will switch to Mandarin again. 我们到了公布得奖名单的时候，我们有请刘登凯刘博士为我们公布得奖名单。
Okay, 谢谢主持人。Okay, Robert, I'm going to give him the list of the awardees and about their questions. So, but I'm going to switch you to Mandarin here as well, and I will come back talk to you in a minute here, Robert. Okay, so 我们这个得奖有2个部分，第一部分就事前得奖的。那我是选了3名哦，第1名是静宜大学化学科的吴振宇同学，他说在设计和开发机器人时候，最重要的技术突破是什么？我想我们他已经知道了，所以这个是非常好的问题。第2个问题是说这个是黄浩伟同学，是大同机械工程系的。那他是用英文的问的，他就主要是问说最大的这个技术挑战是什么，也是类似的东西。那我想就给他这个第2名。那第3名是空军官校张伟那个应该是念陈嘛同学，讲说火星带回来的样本是否有水等等这个问题，所以我就给他这个3名。那至于现场提问的问题，一共是我给了一个4名。那我看一下这个我的笔记本，这第1名是静宜的张义香，应该是他说机器有问题如何维修，这个问题太好了，对我们这个基本上是没办法维修的事情。那第2名是大同大学的这个林冠那是华是吧？他说仪器低温度如何工作，那是他拿的第2名。第3名有2位同学，2位同学，一名是北科大的这个蔡金陈同学，讲翻车怎么办？这个是不可以发生的事情。然后第2个同学是大同的刘应挺同学，说如何发现问题，如何验证，所以这个2个人是第3名。所以感谢同学问非常非常好的问题。And so I'm switching back to English again here, Robert. I really appreciate your presentation. This is a wonderful talk. Let's give Robert another round of applause here. I really appreciate it. I think that, judging based on the question, and I believe you are very popular, we probably should invite you again here, give another talk. And the internet is so good right now. Maybe in the future, sometimes people will be on Mars, listen to your talk as well. If you decide to stay here a little bit longer, or maybe go to Mars as well. So we'll see what happened here to you. Thank you so much, Robert.
Perfect. Thank you, Dan Kai. I appreciate that.
And so let me the contact return to our host.
谢谢刘博士。 好，那我们10月份的讲座将由可再生能源新创公司 C-Trade 的创办人兼 CEO 依照博士主讲。博士致力于研究海洋温差发电技术，他将在他的演讲中分享他从科学家转变为企业家的历程。好，这是我们的10月份的演讲。我们再次感谢 Mr. Robert Hogg 还有介绍人黄友平校长以及此次与会的各个学校同学以及来宾，欢迎大家填写回馈表单，让我们可以做得更好。好，最后呢，我们要感谢这次活动中参与幕后筹备的工作人员、师长、同学。在我念到您的名字的时候，再请师长与同学向镜头挥挥手，让我们可以认识您。我们感谢大同大学的何明果校长，感谢电算中心包昌龙主任，感谢课程林尚林同学老师，感谢录影于佩轩，感谢与我们合作的中原大学张新德老师、叶礼豪主任，感谢东海大学蔡嘉信老师、王崇明教务长，感谢辅英科技大学陈义谦老师，感谢东吴大学秦玉国老师，感谢静宜大学建慈老师与陈明柔主任，感谢民传大学网络电视直播陈春满小姐，感谢台北市立大学陈姿玲老师，感谢慈济大学谢梦平小姐、江允志老师，也感谢辅仁大学周德莲老师，感谢台北科技大学秦先玉老师、潘恩荣小姐，感谢嘉义大学王明宇老师、沈永琪主任、尤建新同学，也感谢本次讲座工作人员，负责各项联络事宜的林小丽、汪东英，负责宣传的吴香宁、林婉莹，以及确认设备状况的林子静。最后感谢大家今天的参与，大胆提问才能成就非凡未来。我们10月份讲座见，谢谢，拜拜。